Hello everybody, it's time for a little regression analysis now that we finished with correlation coefficients. So let's talk regression. So again, we have this really nice set of slides produced by Sir Andy Field and his mites. So we'll use it as a way to kind of guide what we're doing. When we're doing any kind of a regression is a model. So Andy Field likes to talk about models and how we use them to predict points, and that's exactly what we're doing here. Unlike in correlations where we had two variables and we would see how strongly they move together, this time we're actually having one is assumed to be a predictor and the other is assumed to be an outcome. What we call simple regression. There's only one predictor and one outcome. In multiple regression there are more than one predictors and there's still only one outcome variable. But the idea is we'd like to actually have an equation from which we can actually predict somebody's outcome value. So this is an example of his model again with an error, except for this time we have more than one coefficient here. We have this which is called an intercept, right? So if we draw a line crosses the y-axis at some point, and that point's called the intercept. And then we also have a slope to a line. So we're here making this predictive model where x, whatever this variable is assumed to predict y, but it's not going to do it perfectly, right? So there's some error in it. Okay, so if we could predict everything perfectly, that would be great. Like I'm a big Washington Capitals fan, born and raised in DC. And I would have loved to have predicted they were going to win the Stanley Cup this year, but I was like hiding under my bed, curled up like a little baby during those games because I was wanting them to win so bad. I wish I could have predicted they would have won. I would have gone to Vegas before they played the Knights, Golden Knights, and I would have put a bet on them. But hey, that's the way life works. So yeah, so this is what the model looks like, and we'll get into that in more detail later. I talked about slopes and intercepts. Intercepts are where the line crosses the y-axis, and the slope is, or as Andy Field. I'm thinking Philadelphia Eagles here, right? Andy Field likes to call them gradients. So gradient is a slope. So you can have different, same slope because it's the same rate of change, rise over run, as you remember from high school or whatever. That's your slope, but they intersect the y-axis at different points. So they have different intercepts, right? Here you have the same intercept but different slopes. You have positive slope, slightly less positive slope, and a negative slope here. So lots of things can happen in regression. This is one of his examples. It's the one with the record sales. Well, they shouldn't call record sales anymore. Excuse me. Again, I apologize. I'm sick this week. This summer it sucks. So a record company boss was interested in predicting album sales from advertising. Data are 200 different album releases. Outcome variable is sales, either CDs or downloads in a week after release, and the predictor variables are the amount of pounds. Again, he's British. Pounds spent promoting the album before release, number of plays on the radio, and the image of the band. So those would all be predictor variables, right? So here's a look at a scatter plot of the relation between sale in thousands, I guess, of pounds, or is this in thousands of albums? I can't remember. No, I think this thing's albums or whatever. And this is the advertising budget. So we can see that there is kind of a linear relation here, right? Because there's nothing curvilinear here, but you have this scatter plot showing that as there's an increase in advertising budget, there's an increase in sales. So advertising seems to pay off. By the way, for those of you who are interested, we use these models everywhere, not just in public health or nursing or psychology or whatever. They're used in every field, including business and economics. Here's an interesting point that'll come back to haunt us later. Is you'll notice that the variability is greater at the lower end here, right? than it is at the upper end of the scale. Just something to think about later on as we judge heteroscedasticity or homoscedasticity. This is with two predictor variables. As you can see, it becomes more and more difficult to graph these regression models when you have more than one predictor variable. So now this is a plane rather than a line. So we just called linear regression anyway, assuming that, pretend that there's only one variable even though there are more than one variables. And so here's your model. So this model, you have several predictors variables. So you have your intercept. The intercept is generally noted with a 0. Again, this is just notation. I mean, you can use whatever you want, but this is just standard notation for variable 1. You have b1, variable 2. You have b2. These are all the slopes for each of those variables. Notice another important thing: when we talk about the effect of one variable on the outcome, we assume the other variables are held constant. This is important because I talked about controlling for the third variable problem. We do that mathematically by literally holding these values constant when we judge the significance of a predictor variable. So we could say the effect. This is important how to interpret this, because you're going to have to do this in your homework. And again, I'll show you a video on how to do that assignment separate from this. But we'd say each unit increase in X, whatever this variable is, X1, say this is advertising budget, each pound increase in advertising budget would increase record sales by B1, whatever that value is, okay? So that's how you interpret that. Now, it's important to note that you'll notice that there's an I right here behind the X's, right? There's an I next to the Y, and there's an I next to the E, the error term. That means that these are all individual values because there's one value for each individual. Notice there are no I's associated with the B's. So that tells you that this regression coefficient fits everybody. That itself can be a problematic assumption. It's not really dealt with as much in this book, but it's something that I deal with a lot. Okay, what else? Let's see. I'm going to go through all these in a fun fashion. Okay, here's we talk about this method of least squares. This minimizes the distance between the actual values and the predicted values, right? So this is the regression line here. You'll see the vertical distance between those lines. Some are above the predicted line, some are below. That's our total error, right? Observed values minus the model predicted values. Again, so this error term is quite critical here. Let's see. So in terms of judging the model, we will use an F statistic to judge the fit of the model to the data. We talk a lot about fit. And R squared, the R square value is, we talked about that a little while ago in correlations, right? Coefficient of determination. Here the R square is kind of both. What proportion of the variation in the outcome variable is predicted by the predictor variables, but there's other variations of it that are meant to see how well we replicate the population value from the sample value. So they're pretty interesting. Okay. Here's a breakdown of the sum of squares. We'll talk about analysis of variance later, but analysis of variance is used in regression analysis too. So I'm going to skip ahead, let's see, to these descriptions here. So we have a lot of, first of all, we always have variability, right? So, and it's the variability in our outcome variable. The variability, as we did when we calculated variance, we subtracted the mean value from each individual value, right? And then we summated it and squared it. That was a variability. Excuse me. The sum of squares value is the numerator for the variance formula. So the sum of squares total, right? So we just sum and then square. This is called sum of squares, right? We sum the difference between each value of y and its mean value, right? Square it. That's our sum of squares total. We can break that down into a part of it that's accounted for by the model, and our model variability is actually the difference between the difference between the model and the mean. So let me go here. So it's right here. This is the difference between the model, right? This is the model predicted value of y, and this is the mean value of y. So that vertical distance for each one is what we're summing across here to get the sum of squares of the model. So it's telling us how well our model predicts the data, right? Because absent all other information, our best predictor of our outcome would be the mean value, right? The mean is the best model, absence all other information. And then we have this residual. The residual is the difference between each individual value and the predicted value. Okay, so we're breaking down this total variance into these two different components. It's something to remember. It's important, right? Yeah, so there it is right there. And like Andy Field always says, how well your model functions depends on how much better the model predicts than there's error. Part that's not predicted, this F statistic, which we'll be using so F is a different kind of distribution. We talked about a Z value, which follows a standard normal distribution. We have this F value, and this F value is, and you'll see this when we actually do the regression model. It's something called the mean square of the model. The mean square of the model is the sum of squares of the model, which you just saw, divided by its degrees of freedom. And the mean square residual is the sum of square residuals divided by the residual degrees of freedom. We get all those, put them together, we have this F statistic, follows its own distribution. And this is an equation for the R square. You get the sum of square mean divided by the sum of square total. So it's looking at the more proportion, because as you can see, remember the total is the model plus residual. So this is the proportion of the variation, total variation that's accounted for by the model. So that's why you divide it by the total. When we judge our predictors, we use something called a T statistic. Right? A T statistic is similar to a Z standard normal distribution, but a little bit different, has fatter tails. We'll see about that later, but we use this T statistic to assess each of the predictor variables, and it's based on the difference between the observed and expected value. So this is the Andy Field talked a lot about null hypothesis testing. So this is a null hypothesis significant testing issue, because in the null hypothesis our expected value of B is 0. So we're assuming that our predictor variable has no effect. So we want to test whether it has an effect beyond what would be expected. Right? We're expecting there to be no effect. So we have the observed minus the expected divided by the standard error of beta. Remember the standard error. Hopefully you've got that dialed down by now. Right? It's the standard deviation of the sampling distribution of means, right? And it's something like the standard deviation divided by the square root of the sample size in general. Now, here you'll notice that this breaks down to observed divided by the standard error of B, right? That's because our expected value of B is 0, right? So we don't need that. Let's talk about building the model. I'm not going to spend too much time on this because I can show you better, but this is key to your assignment here. So I'll talk about it a little bit. When we build a model, we generally, let's see what we got here. Anything interesting here? Well, let me just mention a couple things. When we build our statistical model, we're going to start by accounting for all the known correlates of our outcome, right? Like if we were, when I had, let me see if that's a good way to do this. Okay, I study smoking, right? And the number of cigarettes smoked is very well predicted by socioeconomic status and race. Those are two very good predictors of smoking status. I could actually break SES down into income, socioeconomic status down into income, and education. So if I put those three predictors and there's a known correlates of smoking, I would account for a good proportion of the variation in smoking. Now, but those aren't very interesting to me because we already know those are strong predictors. I might be interested in something like, say, drive for thinness. do people who desire to be thin smoke more? Because nicotine is a stimulant which would reduce appetite. So, but in order to see if that variable is a significant predictor, I want to account for all the known correlates of smoking first. So if we go back to that formula, okay, so here's the formula. If I'm interested in the effect of this variable, right? Actually, this variable here. So n here stands for, in this case, the total number of predictors, not sample size, right? So this is predictor 10, right? But let's say I want to control for the effects of these ones before I control for 10. So I'd enter these into the model first, and then I would get the proportion of the variation in the outcome that's accounted for by those variables. And then what I'd hope is that this predictor, like let's say here it's driver thinness, would have a significant effect on the outcome, having controlled for all these other predictors, number one, and it would also account for a significant proportion of the variation, given that I already counted for the known predictors of the model. Okay, so that's what we're going to be doing in regression, and that's what we're going to do when we actually analyze our data. Now, there are a couple issues that we have to deal with. One of them is called outliers, and outliers are influential cases. They tend to affect the outcome. Well, they actually affect the model. Here's a really good example of an outlier. I don't know what this is. This is in terms of advertising budget. Some schmuck provided a lot of money, but resulted in very few sales. Now, there's two things that could be wrong here. One is that that's the nature of the data. Somebody's just not very good at advertising, so you have an outlier. Or it could be that the data were entered incorrectly. By the way, you notice that I use plural for data. Data is a plural word, so you say data are, not data is. So this data point may be an outlier, so we'd have to investigate that. Because if you'll notice that if we don't have that data point in the model, this is our regression line. If the data point is in the model, it'll pull that regression line. It'll make it less significant in some ways. Sometimes it could make it more significant, so it's not something that we necessarily want in there, right? Let's see what else. So again here, so number of publications, I have no idea, or number of pubs, maybe actually drinking pubs and death. I'm not really sure which this example is of, but here you'll see that there is a data point here that's very, very out there, very, very out there, and it would extremely affect this regression line, where there's a very strong relation here with number of deaths, right? If you pull this one out here, it changes the nature of the relation. Okay, so we have to investigate these points to see if they're issues for us or not. So we can look at them in two different ways. One is something known as standardized residuals, and the other is Cook distance. So with standardized residuals, we actually calculate the residuals, we standardize them again, so it's like a Z distribution. One thing we know about the standard normal distribution is that 95% of all population values are within plus or minus 2 standard deviations of the mean. So you could always remember this heuristic about the normal distributions. You have 68% between plus or minus 1 standard deviation of the mean, 95% between plus or minus 2 standard deviations of the mean, 99.7% between plus or minus 3 standard deviations of the mean. So any value that's that far away from the mean is like way out there, right? In fact, a value that far from the mean has see if you can figure this one out, has a percentile score of 97.5. Chew on that for a while. Okay, so it means it occurs, it's greater than 97.5% of the population value. So I want you to play with that, see if you can get it. Why? Then there's a value called Cook's distance, which looks at the influence of the removal of a single case. So you should take that case that looks kind of sketchy, take it out of the equation. How would it impact all of the regression coefficients. Absolute values greater than 1 may be of concern. I've also seen values greater than 0.5 would be something that you'd look at. So just keep those in mind. Okay, let's see what else he has here. Let's see some assumptions of your regression. We want to have continuous variables as our outcome variable. Predictor variables doesn't really matter. Now, if you have an outcome variable that's not continuous, there are other types of regression analyses you can use with them. If it's binary, that means there's two levels, like 0 and 1. We use something called a binary logistic regression. If it's ordinal, you can use ordinal logistic regression. If they are not ordinal, but they have more than several categories, but they're not ordinal in nature, like say you have something like I don't know, ethnicity. You can compare African Americans to Caucasians, Hispanics to Caucasians. We use something called multinomial logistic regression. So there's a variety of different kind of regressions. Non-zero variance of predictors, that makes a lot of sense. I mean, if you have no, what's a variable with no variance? Yeah, it's not a variable, right? It's a constant. Linearity, you don't want to curve a linear relation. Independence of outcome values, so you can't have people being related. Let's see, homoscedasticity for each level, each value of the predictor. Actually, I showed you that a little while ago. The variance of the error term should be constant. So the error term is what's not really being predicted, right? Independent residuals, normally distributed errors, and no multicollinearity. Multicollinearity is when we have the predictors being correlated. Okay, let's talk about this multicollinearity for a second. Although I think we're going to get into it in the next slide. You can actually run, and we're going to do this. We'll run these regression diagnostics to show this homoscedasticity using this this plotting of the standardized residuals with the predicted value, right? So that way we can actually take a look at, see if we have variance that's kind of symmetrical across the values of the predictor, normality of the errors. It's assumed that the errors themselves are normally distributed. Multicollinearity means that the predictor variables are correlated very highly with one another. Ideally, what you'd like is that the predictors are completely uncorrelated with one another. So if I have three predictor variables, it would be great if the correlations among them were 0. That means they're not correlated at all. Why? Because we'd like each of those variables to account for a unique proportion of the variation in our outcome variable. That's what we like. We don't want overlap. We don't want there to be any overlap between them. So we want to be as efficient as possible. So there's these heuristics. There's these values like the variance inflation factor. So the variances of the predictor variables are inflated when we have high multicollinearity. So actually, the regression coefficients get inflated when we get a high multicollinearity. So there's something called the variance inflation factor, and any value like that's high, it's around 10 or so, would be considered problematic. Well, if you have high, and tolerance is the opposite of that, so values should be more than 0.2. So these are just a couple of heuristics. One thing you can do is, of course, eliminate whatever variables are redundant. I would start by looking at the correlation coefficients among those variables, and then seeing if they're very high. If you have like correlations around 0.9 or something, that's going to be problematic. So what happens, if we have correlation of 0.9, if we square that, it's 0.81, so that means 81% of the variation is shared among those two variables. So they're very similar, so they'll probably be redundant, right? So what you want to do is remove any variable that's not really providing you any additional information. So you'd like these multicollinearity statistics to be indicating that you don't have multicollinearity. Okay, so we have to look through we have to analyze our data, do these diagnostics to see where we have any issues. So I'm not going to go through all of this now because we can go through this one with SPSS, but here's some examples of what you get when you run analysis. You get this R squared and you get this adjusted R squared. This adjusted R squared is used to say how well the model predicts the population values. So how well your model generalizes to the population. Let's see, anything else here? Here's an analysis of variance table. You have the sum of squares for regression, or the model sum of squares, the residual sum of squares, and the total. This is degrees of freedom for the model. This is the degrees of freedom for the residual. See, 198 plus 1 is 199. This is the mean square. The mean square is sum of squares divided by degrees of freedom. So these two are the same. In this case, in the case of the residual, it's divided by 198, so it's a lot smaller than the mean square model divided by the mean square residual gives you the F value. And this is significant. It's really important that you understand how to read this, because we've been talking a little bit about the significant testing. This value is less than 0.05, it's less than 0.01, it's probably less than 0.001, so it's considered statistically significant. Let's see, here's some examples of parameters, and we'll be looking at this again later. But there uses t statistic to judge for significance. Let's see if there's anything else important here. So here's an example of how you can use these values that are given from SPSS to actually write an equation, right? Write an equation and make a prediction. So if somebody has 100 whatever pound, maybe it was, I don't know how many pounds, it was millions or whatever pound budget, they could expect this many album sales. So you can actually make a prediction for any one value. Let me go back here for a second. The constant was 134.140, and you look here, that's your intercept value, okay? Just so you can see, because I do ask you to write that down. We'll do this Z residual with the Z predictor, see if they have a good figure. Any good figures here? We'll talk all about this later. Oh, here you go, Z residual versus Z predictor. I can't really see which is, I guess this is the residual versus the predictor. It doesn't look like there's any issue here. It looks like if we were to draw a line right down the middle here, you see the residuals, they seem to be scattered very evenly across values of the predicted value, right? So it doesn't look like there's any heteroscedasticity. Normality of the errors. We didn't cover this, or it was covered in your text, but I didn't cover it with you in a video. But this is a way to look at normality. An easy way to look at normality is just to take a look at the histogram and try to superimpose the normal distribution, and you kind of get, oh, looks pretty normal. Maybe there's some leptokurtosis, kind of thin, right? But nothing probably horrible. This looks like it's is this a PP? Yeah, PP plot. So here you were to order all values from lowest to highest and convert them to z-scores, and there's a straight line underneath this which would show you what the values would be, what a normal distribution would look like. Then you convert all of the actual values from that order distribution into z values, and if they match this line, it means they would appear where they would be expected to be if the distribution were normal. So this looks like we have a normal distribution here. Violations of normality will show the actual values being above or below in some bizarre way of this expected value line for normal distribution. And I have a special way I want you to report everything for your assignment, and I'll be covering that in a separate video. Alright, great. I don't want to keep you too long here. Alright, bye.